I have just a few loose ends to tie up about eigenvalues and eigenvectors, and rather than going on and just doing a little bit in the next chapter, this will be kind of a short video. So the setting is we have a matrix A, an n by n matrix, and we've been talking about its eigenvalues and eigenvectors. And one of the things I wanted to talk about is the following. Suppose A is a real matrix. Well, it may have no eigenvalues or eigenvectors. It may have no eigenvalues. And by that I mean no real eigenvalues and no eigenvectors, which is to say vectors in Rn. But of course, a real matrix, we can think of A as being it's also a complex matrix, and it does, as a complex matrix, it has at least one eigenvalue. Of course, we're here, I mean a complex eigenvalue, and similarly eigenvectors in Cn. Okay, so actually kind of an important example is exactly this situation. So suppose A is n by n real, and it has an eigenvalue lambda, and lambda is not real. Okay, then there's a sort of interesting thing which happens, and that's the following. Well, look at the fact that this has an eigenvalue of lambda that says that AV is equal to lambda V for some vector V. And let's take the bar of both sides of this equation. So A bar means you take the complex conjugate of all of the entries of A, and V bar means you take the complex conjugate of all of the entries of V, and so on. So you can clearly take the bar of both sides of this equation, you get this equality. And I said A was real, so A bar is equal to A. On the other hand, lambda is not real, so you can't say the same thing about lambda, and similarly V. But what you do get is the following. You get the original matrix A applied to V bar is equal to lambda bar V bar. And you just look at this equation, and it says that lambda bar is an eigenvalue. The conclusion is that lambda bar is an eigenvalue. So that's kind of a neat thing, which is that when you have a real matrix, if you have complex eigenvalues, they have to come in pairs. So that is to say, the eigenvalues come in pairs, lambda and lambda bar, the non-real eigenvalues. So the conclusion is the following. If A is an n by n real matrix, and lambda is an eigenvalue with eigenvector V, and lambda's not real, then lambda bar is an eigenvalue, and V bar is a corresponding eigenvector. So as I said before, not complex eigenvalues come in pairs, lambda and lambda bar. And a key example of this is this matrix, which I've written down a million times already. My favorite example, this matrix. The characteristic polynomial is lambda squared plus 1, which has solutions lambda is equal to plus or minus I. So if you take lambda to be I, then lambda bar is minus I. And we've already seen that if V is 1I, then 0, 1, minus 1, 0 times this vector is I minus 1, which is to say I times 1I. So that is to say, if lambda is equal to I, the corresponding eigenvector is 1I. And therefore, when lambda is equal to minus I, well, you don't have to solve for the eigenvector from scratch. You know right away that the corresponding eigenvector is just the bar of this one, which is 1 minus I. Well, here's a question. Suppose A is an n by n complex matrix and lambda is an eigenvalue. Does that mean that lambda bar is an eigenvalue? Well, what did I just say? I just said that for a real matrix, this property holds, but I didn't say this is true for a complex matrix. So the question is this property true if you start with a complex matrix? So I'll pause. I suggest that you pause the video and think about this and come back and check your answer. So what'd you get? The answer is obviously no. I'm sure you all concluded that. Why is that? Well, let's just do an example. Let's write down a 2 by 2 complex matrix which doesn't satisfy this. So, for example, take it to be a diagonal with 1 and I on the diagonal. The eigenvalues are obviously 1 and I, and minus I is not an eigenvalue. So why is that? How can that be? Well, the point is that this property is only true for real matrices. The fact that the matrix is real is what causes this to be the case. For a complex matrix, there's no reason why this should hold. Okay. So the next loose end that I wanted to tie up was something about diagonalization. And let me remind you what we said is you have an n by n matrix, and suppose it has eigenvectors v1 through vn, which are linearly independent. And suppose you write the corresponding eigenvalues as lambda 1 through lambda n. Well, A is a map from Rn to Rn, and it's with respect to the standard basis E1 through En. But if you think of A as being a map from Rn to Rn, where you write it down with respect to this new basis, V1 through Vn, then in this new basis, the matrix is simply lambda 1 down to lambda n on the diagonal. That's what it means for a matrix to be diagonalizable. You can choose an appropriate basis, which makes it diagonal. So I did that last time. I just want to say a few more words about it. Okay, let's illustrate this with a very simple example. Let's take A to be this 2 by 2 matrix. It's a 1 here, not a minus 1. The characteristic polynomial is x squared minus 1, which has eigenvalues plus or minus 1. So when lambda is equal to 1, it's very easy to see the eigenvector is 1, 1. Let's call that V1. And when lambda is minus 1, it has eigenvector 1, minus 1. I'll call that V2. And so with respect to this new basis, V1, V2, the matrix is 1, 0, 0, minus 1. Okay. So that's not really anything new. But here's the new thing. There's a 2 by 2 matrix S, which does the following thing. If you take the original matrix, 0, 1, 1, 0, and multiply it on the left by S inverse and on the right by S, what you get is this new matrix like this. So that's the claim, that you can find a 2 by 2 matrix S which has this interesting property. It's quite nice. What it does is it takes the matrix that you started with, which was the matrix of this operation with respect to the original basis E1 and E2, and it gives you the matrix with respect to this other basis V1, V2. And if you think about it for a minute, what you want is that S is supposed to take E1 to V1. Let me write here. S is supposed to take E1 to V1, which is to say E1 to V1, which is 1, 1. And it's supposed to take E2 to V2. And why is that? Well, if you apply, for example, if you apply both sides of this operation to the vector 1, 0, what do you get? Well, on this side, this is the eigenvector here for eigenvalue 1. You get 1, 0 again. And on this side, well, this first operation, S takes 1, 0 to 1, 1. And then that's the one eigenvector for this matrix, so you get itself again. And then S inverse takes you back again. So let me say that over here on the left-hand side. 1, 0 goes by S to 1, 1, which then goes by the matrix 0, 1, 1, 0 to itself, and then it goes by S inverse back to 1, 0. And on the other hand, 0, 1 goes to 1, minus 1, which goes to minus 1, 1, which goes to 0, 1. So that's the guy. And what is S? What's the matrix which does this? Well, if you just think about it, you just put the eigenvectors in the columns. So this is equal to the column V1, V2. 1, 1, and 1 minus 1. Okay, so I'd like to state what's going on here. In general, we have this n by n matrix, and we have this basis of eigenvectors v1 through vn with corresponding eigenvalues lambda 1 through lambda n. And we let S be the following matrix. We take v1 through vn, and you put these as the columns of the matrix S. Then S inverse is equal to this diagonal matrix lambda 1 down to lambda n. Okay. So this is quite a nice property. It says that I've been talking about these two matrices, A and this diagonal matrix, are the matrices of this linear transformation in two different bases, and this is saying that you can get from one to the other by multiplying on the right by this S, as indicated, And this S is what's known as the change of basis matrix. And it's quite a useful tool. We'll see this a bit in the next section. But if you have a problem involving some matrix A, well, sometimes the problem is easier if it was diagonal. So you use S to make it diagonal, and you solve the problem over here, and then you go back again. So anyway, we'll come back and talk about that a little bit. So let me conclude with just a quick discussion of a bit of terminology in the book. The notion of complete from section 8.3, and that's the following. We have our matrix A and its characteristic polynomial, and suppose that the characteristic polynomial factors as follows. It's some constant times lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda n. So you might as well think that we're working over the complex numbers, and that this always happens over the complex numbers. The fundamental theorem of algebra says you can always factor a polynomial of degree n like this. And the lambda 1 through lambda 2 up to lambda n are the roots of the polynomial, and they might or might not be distinct. So each lambda I has some multiplicity n sub I, and that is to say lambda I occurs n sub I times, or in other words, you could write this part of this product. It has n sub I terms, which is to say it's just lambda minus lambda I to the n sub I. So that's the multiplicity of lambda I. And now the definition is that lambda I is complete if the dimension of the lambda I eigenspace is n sub I. So it turns out that the biggest that it could be is n sub I, and it might be smaller. But if it's as big as it can possibly be, you say that lambda I is complete, and you say that A is complete if all the lambda i's are complete. And then it's a basic fact that A is complete if and only if it's diagonalizable. Okay. I'm not particularly crazy about this terminology, so I don't want to belabor it, but the book does use it, and so I wanted to mention it. It's a condition for a matrix to be diagonalizable. We saw before that if all of the eigenvalues are distinct, it's diagonalizable. Well, this is a more general condition. The eigenvalues aren't required to be distinct, but each eigenvalue has to be complete. And let me just leave it at that and call it a day.